Hi, welcome to Qubites, your bite-sized pieces of quantum computing. My name is Renee from Valorem Reply, and today we're going to talk about the progress in quantum machine learning. And for this, I'm very honored to have a special expert guest back, Johannes Oberreuter, and you might actually know him and remember him when we had some previous conversations also about quantum machine learning in Season 1, Episode 6, and Season 4, Episode 1. Hi, Johannes, and welcome to the show. How are you today?
Hi, Renee. I'm very good. Thanks for having me again. It's a great pleasure to be back. How are you doing?
I'm also doing fantastic and, wrapping up the year. Can you tell us a little bit about yourself and your background for those folks that have not seen you on previous episodes?
I'm happy to. My name is Johannes. I'm a physicist by training. I've done a PhD actually in string theory and then two postdocs in two German universities on quantum many-body dynamics before I joined Reply as a data scientist. I'm now co-leading the innovation group for quantum computing, the quantum computing practice of Reply in Germany. And as such, I'm also doing a lot of research into the applications of quantum computing.
Awesome. Yeah. Let's talk about our today's topic, quantum machine learning. And in season 4, episode 1, we already mentioned and talked about QML and related to image classification, in fact. And back then, you were working with your team also on a challenge where, well, image classification was being used. But maybe you can just explain us a little bit more and also tell us what happened since then and any news to share, any learnings to share from that.
Yes, certainly. So back then, the challenge that was posed by BMW and co-hosted by AWS was to classify parts from production from images that were taken by cameras on the production line, whether they are defective or not. And as such, that was not a very novel use of image classification. I would say we have done similar projects with classical computer vision technologies like convolutional neural networks before. But here the interesting thing was to say, well, maybe we can get some extra learnings or some extra benefit from using quantum computing. And to explore this was really, really cool and really interesting in a real world case, which is always more complicated than you would hope for. So this was a really interesting challenge. And our approach there was, well, we are not really expecting to get a benefit, to get an advantage, a supremacy of quantum computing out of this problem, because it is a problem, as I said before, which is not super new. It's something which we have done before. So, and we know that these technologies work very well. So we aimed for something very general and versatile and flexible, something which can which we can use in various circumstances. In that and something, yeah, where we can control the individual parts very much and try to learn something general for quantum computing and machine learning. And the result of this challenge was actually quite encouraging, I would say, namely that the quantum architecture we used or we trained was quite compatible or comparable, competitive, not really competitive, but it was comparable, I would say, with the classical approach. And given the state of the technology, we found it very encouraging. So now the questions, of course, how well would that work in practice, and that is, of course, what we were aiming for. And we have to admit that most of our results we generate in simulators, not real quantum machines. Of course, we also tried the quantum machines, but there are. And that's what makes this field so interesting and exciting. That you have so many topics. You need to learn new algorithms. You need to learn the specifics of the hardware which is there. You need to learn how to handle all these problems. So there's a lot of experimentation going on. So on the one hand, we trained or we evaluated our architecture, our setup with the simulators. On the other hand, we also tried that on the actual hardware. And we realized that, of course, the results on the hardware, with all the errors, with all the noise that you get in practical computations, that the results were worse than on the simulators. So the simulators show a lot of potential. The actual hardware is still something which has problems with noise, problems with availability. But those were all known issues, not something we were surprised about. It was just interesting to confirm that. So, given that, we still believe, or we still work on using this approach and broadening it to more use cases, because the hardware is catching up, right? This is not they're not standing still, and there's a lot of progress going on, and we really want to see the point. You want to be there when the point happens, where the power is there and we can use it. But what we have done meanwhile is to generalize the approach a bit to be more to have the quantum part in this whole hybrid setup. We have a classical part which very much uses or leverages the benefits of pre-trained CNNs, convolutional neural networks, to reduce the compute costs, and then we have a quantum part which helps to embed the state, the information in a quantum state, and make it and hopes to reap some benefits from that. So in this quantum state, you have a lot of parameters to choose from, and it's not necessarily clear. There's one thing which you kind of know you want to increase, which is entanglement. This is this strange behavior of quantum particles, that they can still talk to each other in a way, although they are very far away. And that has been a long controversy in physics. Like, what is this? Isn't this, I mean, Einstein even said, if this is true, this is the end of physics as a science, right? So this strange behavior, but we know it's there, it's measured. There was a Nobel Prize on this actually this year. Zeilinger and other people who have worked a lot on proving in the lab that this state is actually there and entanglement happens. And yeah, I think nowadays it's accepted and we understand why it's happening. But this is the thing, the resource of quantum computing which you want to produce. And it's kind of known how to do that, but there are various ways. And for different data, different ways of doing that might be an advantage. And we've worked towards making that easier in our setup to exchange the quantum circuit and to benchmark various quantum circuits against each other. So again, for the image classification, there was not much of a benefit of doing that, as we realized. I was a bit surprised about that. I thought that we would at least see a drop for certain architectures, but that didn't happen. So now the next step is to try it on various other tasks. What we are currently looking into is something like sensor data. That would be certainly something I'm super interested in to see. But we're also looking at the classical part of this whole setup. So I said convolutional neural networks is something which is established and which is kind of used widely in image classification tasks. But there are new developments also on the side of machine learning. We have transformer models, if that rings a bell, and they have shown astonishing capabilities of modeling language, for instance. That was the aim for which they were set up. So, but it has been shown recently that transformers can also take image classification tasks, which is super surprising. That an architecture which was focused at one thing would be so efficient at other tasks as well, which is in a way what we also try to achieve with our quantum model, right? So now the question we're also looking into is in how far could you use pre-trained transformer models, and they're huge models, right? They are the millions of parameters, and it costs millions of dollars to train them. They're really, really huge models, and you need to have pre-trained models. So this is another thing which we're looking at. Can you combine this new technology on the classical side with our idea on the quantum side? So now we have been talking about one aspect of machine learning, but I already mentioned language, and of course, machine learning is a very, very broad field with a lot of applications. Especially in the area of language modeling, there has been for a while an activity by people in Oxford who have an idea that language is something which inherently, if you combine the meaning and the grammar, something which inherently should be modeled on a quantum computer. And this is a very on the opposite to what we are trying or what we have been trying so far, to model something or to use a model which is very versatile, very general, something very specific. You look at one problem and then again you try to solve this specific problem on a quantum computer. And this is something which is interesting now, because we would like to see if we are if you're adopting this approach, if you're coming from the other side, so to speak, and trying to devise some specific models for specific applications like languages, also for images, by the way, because you can do a similar thing where you're devising quantum filters specifically to the images. If that would be if then it's easier to reap an advantage. The downside is, of course, you have to do it for every problem again, or for every problem class, but it is something which is not which might be an advantage, and we haven't experimented a lot with that yet. That is something we are going to do in the future, and which we have started.
Also, and you already mentioned what is the latest research of QML-based classification. You already talked about the hybrid approach. Is there anything else you want to talk about there?
I think it's quite important that now we get a deeper understanding and a grounded understanding on which technologies to use in which case, similar to what we a level of understanding we have in classical machine learning. Classical machine learning, if there's a problem, most engineers, most data scientists
Mhm.
would kind of come up with a similar solution, and they would say, okay, look, in this setup you have these two possibilities, you can do these architecture, that's new on the market, that's what you should try. And at the moment, I would say for quantum, this is not so much the case yet. There are a few cases where we kind of understand what to do, but in for especially in quantum chemistry, for instance, there's a lot of stuff where we understand that quantum computing can give an advantage. But for quantum machine learning, my feeling is that it's not. We are trying we are trying to look around and apply it to everything, but I don't believe that everywhere there's an advantage. We should understand where we can really benefit from which setup of quantum computing.
Mhm.
And in order to do this, I think we need a structured way of benchmarking use cases and benchmarking architecture. And the interesting thing is, and again, that's what it makes so exciting. New things are coming every day or every month.
Yeah.
Let's not exaggerate, but it's very often that there are new startups coming up, new strategies to do architectures, new money coming into the field. So new developments also on the software side, SDKs which are there. So what I want to say is it's not that we kind of understand how this field will look in 10 years. We don't at all. And it is very unclear if a specific approach to implement quantum computation would improve the situation suddenly and would reduce the noise, would be better at the error correction, error handling. So all of these things is something we need to understand. How do certain developments on the hardware side, developments on the software side, and especially the algorithmic side, how to implement a specific machine learning algorithm, how do they cooperate to reap benefits which manifest themselves in a specific use case. And for this, we are currently collaborating with some other research institutes and some industry appliers um, who are interested also in benchmarking specific use cases and providing a framework in order to do this in a structured way. And there's more to come. It looks very nice, but we hopefully are going to collaborate on this for quite a while. It's almost decided, but not quite official yet. But I'm super excited about this development, because I think for the industry this will be a big advantage if you kind of have a box in where you can put your use case in. It will more or less spit out, okay, for this I have good reasons to recommend this architecture, and that will also help us to understand better how to do that.
Yeah. And actually, let's continue on the topic a bit, and also talk about the long term version of quantum computing. Also, what we're doing at Reply, and any thoughts there?
Yes. So at Reply, this is one of the activities we are excited to get involved in. And on the other hand, of course, we are doing consulting. We have clients. We are helping our clients with our insights. So we are having come from a very broad approach where we have researched all kinds of applications and all kinds of trends. I would say we are now in a position where we can start shaping an offering for individual industries. And one of the industries always has been, and it's a very interesting industry for quantum computing, is the financial industry. There we are doing some research with clients, but we also have some algorithms with which we have had some hands-on experience now, which we can really offer to our clients to implement and help them to put even in production with quantum-inspired architectures, like where we use simulators again to apply the quantum algorithms. But so the financial industry is certainly something where we have where we can shape or we have shaped an offering which we can now with which we can now approach the market. By the way, we are finalizing a paper on portfolio optimization with a very specific usage of this. So we show some tweaks and tricks which we uncovered and which we came up with in order to make your life easier, which could be interesting to the industry as well. So in this direction, we are still working a lot, but other industries would, for instance, include automotive, or let's say engineering, maybe a bit more broadly, because a lot of the problems are similar for say aviation, automotive, and there are a couple of things. Of course, one of the topics which are relevant there is the whole idea of material simulation. Very interesting for all engineering applications. Another approach or another problem is machine learning, of course, as we've already done. And well, along with material chemistry simulations, making batteries, all of these things is something which we are where we have developed some example cases already, which we can now offer to the market. So I would say the news is here that we are trying to, or we have enough experience so we can focus on specific industries somewhat better. Yeah. So and the other thing is, of course, we keep contributing to the development. I mentioned the activities in benchmarking. I mentioned the paper. So this is something which we keep contributing, and we see, as I said, this is developing, and I don't know what's going to be interesting next year. But of course, we are continuing with along the lines of our experience so far, and we are taking on whatever the research community is offering and whatever the new insights will be.
Yeah. And like you said, it's so fast, and so many things are happening. And also on the topic you just mentioned about quantum chemistry, I had a really impressive conversation with Shahir Kainan in episode 6 of season 6, when we talked about personalized medicines that they're developing and shortening the path to for drug discovery, making something that took like 4 years, they can now do it in a few months using a quantum optimization, and it's life changing for what could potentially be life changing for people. And it's impressive how fast it's going. And like you're saying, we'll see next year, right? What other things will be happening there. And yeah, it's a really fast paced industry and impressive.
So it's also always a good idea to be skeptical, I would say, because you're, especially on our side, we are not completely independent of other players in the market, right? It's not like you can say, okay, if there are no more of this kind of GPUs, we buy other ones, or if this cloud vendor goes down, we go to another one. There is a lot of startups, but it is not established enough that we can be super confident that or entirely confident that the hardware will be there. This is the exciting thing, that we co-developing at the moment, hardware and software applications. But while it's good to be skeptical or to have that in mind, it is also good to understand that those players who are in the market have been delivering so far the progress they have been promising. And if this continues, of course, I mean, results in the past are never a guarantee for the future. But if this continues in the way which we have seen, and I have at the moment no reason to distrust those people, then really in 2025 we'll be at the point where we can run applications on a quantum computer in an industry setup. At least that is what the vendors are envisioning. So sure, I mean it's not, this is not in our hands. We are not doing the hardware, and I cannot promise this, but this is what I'm working with as an assumption, because I feel that the vendors are trustworthy so far, and that 25 is not so far in the future, right? It's 2 more of these episodes of these wrap up the year episodes, and we are there. Of course, if it's a year later, it's a year later. But the point is, it's something within our, we'll know within our professional lifetime, right? It's not something which is, oh, maybe in 30 years, maybe in 50 years, maybe in, we don't know. This might become a reality. It's something which we will know if it works and how it works within our professional lifespan, and really in the near future, I would say. And yeah, I think we see that getting these processes, these new technologies into organizations is tricky. There's a lot involved in terms of identifying the cases. And that's again why we do the benchmarking, because we want to help identifying the cases where it can be useful. That you understand how to do the procurement, that you understand the safety concerns, that you get the people involved and educate more people on how to implement the algorithms, learn the languages, learn the way to do this. I mean, there's a lot involved, and that can easily take this time. And this is why we have been on this topic already for a couple of years, and why we're excited to help our clients to understand what the benefits of the technologies can be for them.
And it's a very much a very much a topic that is very much current. And you mentioned the Nobel Prize in Physics that went to Anton Zeilinger and John F. Clauser and Alan Aspect for
Yes.
basically pioneering experiments with entangled photons and proving that entanglement is not just a theory. And then just like, when was it, last month or so, there was another new paper published, and also they had a big article on Quantum Magazine about this, wormholes that they simulated on the quantum computer, and basically showing the ER equals EPR duality, basically showing that wormholes and quantum entanglement are the same thing. And yeah, it's impressive, like the progress that is happening. Like you're saying, in a couple of years, we will really know much more, and it's not unlike nuclear fusion, which, like you're saying, might take like decades. This year we will know much more in a couple of years, and yeah, super exciting time.
I'm trying not to look down to any other technology, because also they have a really difficult problem. This is very interesting, because you know that nuclear fusion works, right? You look at the sun, you know it works. It's just really difficult to simulate it. Very similar with quantum mechanics. You know it works because we have atoms, because we have nuclei, because we have fundamental particles. All of that is there. We know it works, but to do it artificially has proven tricky. Now, as you said, the Nobel Prize kind of honored the people who showed us that at least the mathematical framework is correct, and correct to the point where it's a useful model, at least, and we can work with that. And in practice, a lot of the philosophical implications of quantum mechanics, that this is what drives people like Anton Zeilinger, right? He says there's something we need to understand better, and he's right. We should understand that better. But very often, from an engineering perspective, you can still work with things where you don't understand all philosophical underpinnings, right? You can still work with it because you understand the mathematics and you know how the systems behave. And yeah, like with fusion, it has proven super difficult to get this system into a stable state. And in a way, we are at the same point with quantum, right? Now you want to get a big system which you can really use, which can deliver the power, like the fusion reactor should deliver the power. And there are problems, but there's a lot of people and there's a lot of ideas. That's maybe something different from fusion. That you have all these startups, you have a very rich universe, you have a lot of ways, because quantum effects are so universal. You have a lot of ways to implement quantum computing, and that's why I'm a bit more. It's not as expensive also than to build a fusion reactor. So that's why I'm a bit more hopeful and confident that quantum computing should make a good development on the hardware side, or at a faster pace, let's put it like this. But yeah, fusion is also, of course, a problem. Ideally, would be we first build the quantum computer, and then we help solving the nuclear fusion, the energy problem, which, by the way, is like describing fluid dynamics and these things is one of the applications of quantum computers, which we're also looking into.
Yep, yep. In fact, like you're saying, computational fluid dynamics. I also had a conversation with a guest here in Qubites a while ago about actually using it, and using quantum computing for that kind of stuff. And yeah, like you're saying, we use this technology as another tool in our tool belt to
Yes.
solve these exponential complex problems. And it will be an amazing tool once we have it. Anyhow, we're already at the end of the show here. Thank you so much, Johannes,
It
for
was a
joining us
pleasure.
today.
Thank you very much for taking the time to talk to me. I enjoyed.
Thank you so much. Very much appreciated. And thanks everyone for joining us for yet another episodes of Qubites, your bite-sized pieces of quantum computing. Watch our blog, follow our social media channels to hear all about the upcoming episodes, and of course, subscribe to our YouTube if you want to get all the notifications when the new episode is available. And of course, you can also watch the previous episodes, the ones with Johannes and all the other guests on our websites. You can find them all there, including a full transcript for each episode. Thank you so much. Take care and see you soon. Bye bye.